Hi everyone. So in today's video, we're going to be learning a few new formulas that will allow us to evaluate sine and cosine of two angles added together or two angles being subtracted. So I want to just kind of show you what is the type of situation where you might want to use an angle addition or subtraction formula. So it might be something like this. So let's say you were asked to find the exact value of sine of 75 degrees. So when we say exact value, that means that we don't want a decimal approximation. We want something that's like square root of 3 over 2 rather than, 0.1329 or something like that. So we want an exact value. The problem is that 75 degrees is not one of the nice friendly angles we know on the unit circle. So the trick that we'll be doing in this part is when you see something like sine of 75 degrees, sine of 75 degrees is the same as sine of 45 degrees plus 30 degrees, right? Like 75 is the same as 45 plus 30, so we can split that 75 up. And so what we'll see today is that there's a special formula that allows you to evaluate things like this. So today we'll be looking at there is a formula for this. So we'll get to that in a few minutes. Before we get to the actual formula, I want to tell you what the formula isn't. So it would be very tempting to think, so I'll put my little warning symbol to alert you that this is not the correct formula. It would be very tempting to think that if you have sine of two angles being added up. So I know we typically use things like theta for angles, but in this section, we're just going to use capital A and capital B. So when I write sine of A plus B, that just means something like this, something where you're taking sine of two different angles being added up. So it would be really nice, right, if sine of A plus B was equal to sine of A plus sine of B. However, that does not work. That formula does not work. And we can actually very easily show that this formula doesn't work. So for example, let's say you wanted to find sine of 30 degrees plus 30 degrees. So I want to be clear, this is not an actual place where you would use the angle addition formula. Because 30 plus 30, we know that that's 60, right? So we actually already know what the answer should be. Right? So what should sine of 60 degrees be? Well, if you go on the unit circle and you go to a 60-degree angle, pardon my bad drawing here, but if you go to a 60-degree angle, we know that the y-coordinate is root 3 over 2. So we're kind of using this as an example to check whether this formula works or not, because we know what the answer should be. And if we try to use this formula and we get something else, that tells us that it's not the right formula. So if we try to use what we wrote above here, then that should mean that if you do sine of 30 plus sine of 30, you should get the right thing. However, what is sine of 30? Well, I just erased my unit circle, but 30 degrees would be like that, right? And so sine of 30 is 1/2. So what is sine of 30 plus sine of 30? It's 1/2 plus 1/2, which is 1. And that's not correct. That is not the correct value for sine of 30 plus 30, because we know that 30 plus 30 is 60. So we already know what sine of that angle should be equal to. So clearly this formula does not work. It is not true that to take sine of the sum of two angles, you can just take sine of each angle individually. So what is the actual formula? Well, here it is. So let's say that you wanted to take sine of an angle A plus an angle B. So the formula basically kind of blends together sine and cosine in an interesting way. So you start by taking sine of your first angle, so sine of A, and then you multiply that with cosine of your second angle. So you're kind of blending together your sines and cosines. Then to that you add cosine of your first angle times sine of your second angle. So you're kind of like blending things together every which way, right? You're in the first part, you're doing sine of the first angle, cosine of the second angle, and then in the second part, you're flipping them. So it's like every different sine and cosine happens with every different angle. So this is the angle addition formula for sine. So we'll do an actual example using this in a moment. We'll actually do the example that we started at with the one in purple. But I just want to first kind of demonstrate to you that this formula works. So how can we check whether this formula works? Well, we can do this problem up here, right? We already know that sine of 30 degrees plus 30 degrees should give us the same thing as sine of 60, right? So we know it should give us square root of 3 over 2. So if we apply the formula that we have above, we would get sine of 30 times cosine of 30. So in this case, because the two things you're adding up are the same, you don't get the A and the B different as kind of shown in the formula above. And then we have cosine of 30 and we have sine of 30. And so what is sine of 30? Well, let's just draw a 30-degree angle on a unit circle again so we can look at this. So if you go to a 30-degree angle, we have square root of 3 over 2, 1/2. So sine of 30 is the y-coordinate, which is 1/2. Cosine of 30 is square root of 3 over 2. And then here we get the same thing. So then we have cosine of 30, so that was square root of 3 over 2. And then we get another 1/2. So if you add these up, you end up with square root of 3 over 4 plus square root of 3 over 4, right? Because when you multiply two fractions together, multiply the numerators, multiply the denominators. And so that gives you 2 times the square root of 3 over 4, which is the same thing as square root of 3 over 2. So that agrees with what we know the actual value of sine of 60 is. And so that just kind of demonstrates that, okay, this formula makes sense. It works at least for this one example. So I now want to do an example of like actually using this formula. So a place where you actually would use this formula, because again, you don't need to use this formula to find sine of 30 plus 30, right? Sine of 60, we know how to do that without using this formula. But in a situation like this one, so if you were asked to evaluate and find an exact value for sine of 75 degrees, you're kind of forced to use this formula because we don't know exactly, like if you go on the unit circle and draw an angle of 75, that's not one of the ones that we know. So we don't know that exact value unless we split it into 30 degrees plus 45 degrees, or maybe, let me be consistent. Up here I wrote 45 plus 30, so let me just write it that way. It won't matter which way, but. Okay, so let's apply this formula. So how does this formula work? Well, we're going to do sine of the first angle and then multiply that with cosine of the second angle. And then to that, we're going to add cosine of the first angle and multiply that with sine of the second angle. Okay, so let's draw a little unit circle here. So we have all the information we need. So we need sine and cosine of both 45 degrees. So 45 degrees, we would have square root of 2 over 2 and square root of 2 over 2. And then for 30 degrees, we would have square root of 3 over 2 and 1/2. Okay, so sine of 45 degrees is square root of 2 over 2. And then cosine of 30 is square root of 3 over 2. And then cosine of 45 is square root of 2 over 2. And sine of 30 is 1/2. So if we multiply these together, so one thing about square roots that you're going to need to know in this section is if you have something, and maybe I'll like write this off to the side here. So in general, if you have square root of a times square root of b, you can rewrite that as square root of ab. So square roots kind of can be multiplied into each other like that. So in this example here, if we have square root of 2 times square root of 3, that is equal to square root of 6. So we have square root of 6 over 4 plus square root of 2 over 4. And so if we add those together, we get square root of 6 plus square root of 2 divided by 4. So if you were to type sine of 75 degrees into your calculator, it would give you a decimal approximation. And that decimal approximation is an approximation of the value that we just found here. So you can even test that out for yourself. Type sine of 75 into your calculator, see what you get, and then type this thing that we just found here into your calculator, and you should see that it gives you the same approximate value. But this is the exact value. Okay, so we now know the formula for sine. There's also an angle addition formula for cosine, and unfortunately it's different. So for sine of two angles being added up, you kind of blend doing sine of one times cosine of the other. The cosine formula is kind of the opposite of that. So the cosine formula says that cosine of two angles A and B being added up is equal to. So for the cosine formula, you start by taking cosine of your first angle, and then you multiply that with cosine of your second angle, so cosine of A times cosine of B. And then from that you subtract sine of your first angle times sine of your second angle. So it's really different from the sine formula in a few different ways. One way is that you're now, like in the sine formula, you have sine and cosine kind of side by side and side by side, and then you're just changing the angles and then you're adding them together. Whereas in the cosine formula, you're doing cosine times cosine and sine times sine, and then you're subtracting them. And another thing to point out, so personally, I find the sines one a little easier to remember just because it's kind of hard to mess it up. You could switch the order of like any of these things and it's not really going to matter, right? You could write this instead as like cosine of B times sine of A, right? The order isn't going to matter. And then you could switch the order that you're adding them up, right? Because adding two things up, it doesn't matter. 3 plus 2 is the same as 2 plus 3. Whereas for this one, you do have to make sure that you do the cosine part first, because when you're subtracting two numbers, the order does matter. So 3 minus 2 is different from 2 minus 3. So just be sure that with the cosine formula, you know that the cosines are the part that comes first. Okay, I want to do a couple more examples. So we'll do one example, another example with the sine formula, and then we'll also do one with the cosine formula. But I want to do these other examples with slightly trickier angles. So the one that we did just now was 75 degrees. So at least for me, 75 degrees, it's not too hard to see, okay, that's just 30 plus 45. But some of the other angles that we're about to do are going to be angles where it's a little bit harder to see exactly like which angles you can add together to get them. So what I want to do is just quickly fill out a unit circle with some of the most important degree measures. So, I think this whole quarter we've been really emphasizing radians. In this section, we're mostly going to be dealing with degrees. And the reason for that is that it's just a little bit too hard, in my opinion, to be able to figure out. So like what we just did is we said, okay, 75 degrees is equal to 30 degrees plus 45 degrees. Like you can just kind of look at the number and figure that out. If instead I had given you 7 pi over 12, which is the same thing as, or actually, sorry, that's a different angle. Maybe let me do the same angle just for continuity. Let's see. So if I gave you, actually, whatever, let's stick with this. This isn't 75 degrees. This is 105 degrees. But my point is that I don't think, at least for me, I don't look at this and say, oh, I know exactly what angles to split that up into. It turns out that it splits up into pi over 3 plus pi over 4. But like, I think it's a lot harder to to determine that just by looking at it. And so that's the reason that I'm not really doing these with radians, just because I think it adds in this whole other element of having to be able to take a fraction and figure out what fractions it came from. So we're going to be focusing on degrees. But that being said, I think probably most of us aren't as familiar with all the degree measures of the important angles on the unit circle. So I just want to quickly write those down. So 30 degrees, that one's not too hard to know. So this is 30 degrees. I'm not going to put the terminal point. I'm just going to put the angle. So that's 30 degrees. Here we have 45 degrees. Here we have, I'm not drawing this super well, but that's okay. 60 degrees. Here we have 90 degrees. So the next angle is going to be 90 plus 30. So that's 120. And then the next angle is going to be 90 plus 45, so that's 135. The next one is going to be 90 plus 60, so that's 150. Or you can think of it as being 180 minus 30. So the next one is 180. Then we have 180 plus 30, so that is 210. Then we have 180 plus 45, so that's 225. Then we have 180 plus 60, so that's going to be 240 degrees. Then this one is 3 times 90, so that's 270. Then if we add 30 to that, that gives us 300 degrees. And let me fix this because I'm going to run out of space. 270, 300, just a couple more. So then we have 270 plus 45. So that's going to be what, 315 degrees. And then we have 270 plus 60. So that's going to be 330. And then that's it. So the reason I wrote all of these down is because we're about to do a couple of examples where I think being able to have this reference will be able to kind of help us figure out what angles we can use. So let's say, for example, that you wanted to evaluate, oops, my screen is not moving. There we go. Let's say you wanted to evaluate cosine of 165 degrees. So basically, we want to be able to figure out what angles might we be able to use from this that would help us. So personally, I just start looking at angles and try to see, what would I have to add to that to get 165? So there's actually, there's probably many possibilities here, but the first one that jumps out to me would be, okay, we can write 165 as 135, oops, plus 30. You could also do it as 120 plus 45 degrees. And I'm sure there's other ways that you could come up with it as well with these angles. But let's do it with 135 plus 30. And then I would encourage you to try it this way or try it some other way and verify that you get the same answer, because you should. It will, like the steps leading up to it will look different, but in the end you should get the same answer. Okay, so let's stick with this one. So how does the cosine formula work? Well, it says you take cosine of one of your angles, and then you multiply that with cosine of the other angle. And then from that you subtract sine of your first angle times sine of the second angle. Okay, so we're going to need to know cosine and sine of 30 degrees. So let's put in that terminal point for 30 degrees. So it's square root of 3 over 2, 1/2. And then we're also going to want to know it for 135. So for 135, 135 is like a 45 degree angle, but in quadrant 2. So it's going to be negative root 2 over 2 and positive root 2 over 2 as the y coordinate. Okay, so that tells us that cosine of 135, so we're looking now at this angle here, cosine of 135 is negative square root of 2 over 2. And then cosine of 30 is positive square root of 3 over 2. And then from that, we need to do sine of 135. So sine is the y-coordinate at 135, so that's square root of 2 over 2. And then we're multiplying that with sine of 30, which is 1/2. So if we put all of this together, we get square root of, or negative square root of 6, rather, over 4, minus square root of 2 over 4. And so we can combine this into one function, or one fraction rather, and this would be negative square root of 6 minus square root of 2 divided by 4. And again, if you want to check this, you can check by typing cosine of 135 into your calculator, and then separately typing the answer we just found into your calculator, and they should have the same decimal approximation. All right, we're going to do one more kind of along these lines. So the next one we're going to try is going to be going back to the sine formula. We're going to find sine of 255 degrees. So first thing we want to do is figure out how can we write 255 as one of the, two of the angles from this picture being added together. So again, there's like many different ways we could do this. To me, maybe the most obvious one would be 225 plus 30. And that's nice because we already have the stuff for 30 written down, so we won't have to do it again. So 225 plus 30 gives us 255, which is the angle we're looking for. So let's put in the coordinates of this one. So the angle 225 is a 45 degree angle, but in quadrant 3. So it's going to be negative root 2 over 2, negative root 2 over 2. So let's go and put this stuff in. So sine of 225 is going to be equal to sine of, 255 is going to be equal to sine of 225 plus 30. So how did the sine formula work? Well, basically we just kind of blend together sine and cosine. So we do sine of 225 times cosine of 30 plus cosine of 225 times sine of 30. Okay, so looking back at our picture, sine of 225 and cosine of 225 actually are both going to be negative root 2 over 2. So we're going to have negative root 2 over 2 for sine of 225, and then again later we'll put that in for cosine of 225. Cosine of 30 degrees is our x-coordinate, so it's square root of 3 over 2. And then cosine of 225, as we mentioned, that is equal to negative root 2 over 2. And then sine of 30 degrees is our y-coordinate at our 30 degree angle, so that is equal to 1/2. So altogether, and again, my screen is not scrolling, there we go. Altogether, we get negative, and I didn't plan for this, but actually you might notice something interesting. So we get negative square root of 6, maybe let me not jump a step ahead. So negative square root of 6 over 4 minus square root of 2 over 4. So altogether, that's negative square root of 6 minus square root of 2 over 4. So you might notice that that's the same as what we got in the previous question. That's okay, right? There can be multiple angles that have the same sine or cosine value. So maybe let's try to figure out why that is by looking at the picture. So the first angle we were looking at is 165. So where is 165 on the unit circle? It's like here. And we were finding cosine of it, so we were finding the x-coordinate of that angle. And then the other angle we were looking at was 255, and that's over here. And we were looking for the y coordinate of that because we were looking for sine. And just by kind of looking at the symmetry, I think you can buy the fact that the x coordinate of the blue angle is the same as the y coordinate of the purple angle. So in general, when you do these problems, your answers are usually going to look very similar. And the reason they're going to look very similar is because they're always using the same building blocks. They're always using these, you're adding up angles that have either square root of 2, square root of 3, 1/2. Those are really like the only numbers that you're working with. And so your answers will always look something like this. And it's just for these two examples, they actually happen to be the exact same number. And that's fine. There are definitely many angles that have the same sine or cosine values as each other. Okay, I want to do one more example along these lines. Actually, sorry, let's do something else first. So the next thing we're going to do is come up with some rules that allow us to work with subtracting angles. And so if you know, like what I would recommend is memorize the rules for angle addition. So the ones that we already had written down, I'm just going to write them down again. If you have those memorized, then you can easily come up with the rules for angle subtraction from the one from addition. And I'll show you what I mean by that in a second. Okay, so here's our addition formula. So cosine of A, sine of B, and then our cosine formula. So cosine of A plus B, we had cosine of A times cosine of B minus sine of A times sine of B. Okay, so how are we going to come up with some rules for angle subtraction? Well, basically, we can just use our rules for angle addition and kind of put in a negative angle. So we're going to kind of do that below, and then once we've figured out what the formula is, we'll come back and write it up at the top so that we have all four of them kind of written together. So this is kind of like in the last video that we did, or the video we did, yesterday, I think. I'm losing sense of time. But in one of our recent videos, or it was 2 videos ago, I gave you one Pythagorean identity, and we used that Pythagorean identity to come up with 2 other ones. And this is going to be a similar idea. So we're going to derive the angle subtraction formulas. Okay, so how would we do this? Well, if you wanted to figure out a formula for sine of A minus B, we could instead write that as A plus negative B, right? A minus B is the same thing as A plus negative B. And so if we go and write that all into our regular addition formula, we'll have sine of A times cosine of negative B. So sine of A, cosine of negative B, plus cosine of A and sine of negative B. So this is fine, but we want to make this formula so that it only has A and B in it. We kind of want to get rid of this negative B. So how can we do that? Well, we know we have these even and odd identities, right? So we know that cosine of negative B is the same thing as cosine of B, right? Because cosine is an even function. And then for sine, well, sine of negative B is actually going to flip signs. So this is going to be cosine of A times negative sine of B. And so a nicer way to write this would be sine of A times cosine of B minus cosine of A times sine of B. And so for the subtraction rules, you actually do need to pay attention to the order that you're doing stuff in because you're subtracting. So it's important that you first start by taking sine of the first angle, and then in the second part, that's where you take cosine of the first angle. So again, just to recap, where did this come from? We basically just tried to make an adjustment to the addition rule by, instead of putting b, we put a negative b. And then we use the even and odd identities to kind of like get rid of that negative b. So now we have a nice formula that will just allow us to just plug in our original a and b. So I'm going to add that to our list. So sine of a minus b is going to be basically the same as what we had for sine of a plus b. The difference is that now you're subtracting between them. And that subtraction basically came from the fact that sine is an odd function. And so that's where that negative sign appeared from that first one, when we factored out the negative sign basically from the sine, because sine is an odd function. Okay, so last of all, let's do one for cosine. So if we do the same thing, if we take cosine of a plus negative b, and just kind of force that negative b into the formula, and then see how we can then adjust the formula. So we know that the angle addition formula for cosine does cosine of both angles together, and then it does sine of both angles. So that is going to be cosine of a times cosine of b, and then, and this is negative b, right? Because that's what we're plugging in. So another way to write cosine of negative b, as we talked about in the last one, because cosine is an even function, cosine of negative b is the same as cosine of b. And then sine of a stays the same, and then sine of negative b, well, that's the same thing as negative sine of b. So now we can rewrite our formula, and it's going to be equal to cosine of a, cosine of b. Now it becomes plus, because we have a negative times another negative, sine of a, sine of b. So, what's going on here? Basically, these formulas look just like the addition formulas. It's just that we are flipping the sign in them, basically. But again, if you don't want to crowd your brain with remembering all four of these formulas, if you can just remember the first two, then you can easily figure out these other two just by doing what we did below. And then same thing goes, so in tomorrow's video, we'll look at a couple of formulas called the double angle formulas. And again, those are just going to rely on these first two. So really the first two that we wrote down are definitely the most important ones to know. Let me just get this written down, and then we will try some other examples. Okay, so A, B, B. So basically, this is the main kind of takeaway from this video, is these four formulas. And you don't need to go through all the steps of doing what we did below, but if you do forget the bottom two, that's always there as a possibility. Okay, so I want to do a few more examples. So I'm going to keep going on this page. So let's evaluate cosine of 15 degrees. So for this one, we're going to actually end up using an angle subtraction rule, because we don't know how to write 15 as, an angle plus another angle, but we can write it as 45 minus 30. So let me put those side lengths in here. So we're going to rewrite this as 45 minus 30. So now we need to remember the angle subtraction rule for cosine. So basically what we saw on the last page was that it's the same thing as the angle addition rule, except for now we're adding instead of subtracting, because the sine part flipped around the sine SIGN. So cosine of 45 is square root of 2 over 2. Cosine of 30, we've seen that one a few times now, that's square root of 3 over 2. Sine of 45 is, again, square root of 2 over 2. And then cosine of 30 is going to be, oops, I did something wrong. This should be a sine, right? So the cosine formula should have cosine and cosine and then sine and sine. Sorry about that, my bad. So sine of 30 is 1/2. So again, you might be like, okay, at this point I've seen these numbers a bunch of times, and it's true. It's going to be very similar to the other ones we did. So we'll get square root of 2 over 4 for the second part, and then altogether that is square root of 6 over 4 plus square root of 2. And actually, let me make this one fraction. So let's also do sine of this angle. I lost track of which colors I've used and not used. Let's use green. So we're also going to find now sine of 15 degrees. So we can rewrite 15 degrees as 45 minus 30 like we did in the last one. And hopefully you're now aware of this, but I always forget to say, I definitely would encourage you to pause and try this yourself to kind of test yourself. You can go rewind and go look at the where I wrote down the formulas and see if you can finish this off yourself. So what is sine of 45 minus 30 degrees? Well, the sine formula, we're going to take sine of 45 degrees, and then we're going to do cosine of 30 degrees. And then to that, we're going to subtract cosine of 45 degrees times sine of 30 degrees. So that is going to give us, again, square root of 2 over 2 for sine of 45, cosine of 30, that is square root of 3 over 2. And then we'll subtract from that, cosine of 45 is square root of 2 over 2, and sine of 30 is 1/2. So same kind of building blocks as in the last one, just in a slightly different order. So now we'll get square root of 6 over 4 minus square root of 2 over 4. So our answer is just slightly different from above. It's now square root of 6 minus square root of 2 all over 4. So again, very similar looking to some of the other ones. All right, one more example I want to do on this same note, and then we'll do one kind of slightly different variation of this, and then that'll be it. So the next thing I wanted to look at was tangent. So let's say that you were asked to evaluate tangent of 15 degrees. So there is an angle addition and an angle subtraction formula for tangent. However, I'm not going to really teach it because I just don't think it's worth adding another thing to the list that you want to have memorized, because you don't really need that for tangent, right? For tangent, you can always write tangent as sine over cosine. So tangent of 15 degrees is going to be equal to sine of 15 degrees over cosine of 15 degrees. And in this case, we already found sine and cosine of 15 degrees. But if you hadn't found them yet, so if this asked you to find tangent of one where you hadn't done it yet, well, now you know how to do sine and cosine, right? So you could do sine and cosine each individually using angle addition or subtraction. And so we found that sine of 15 degrees, that's one that we just did. So that's square root of 6 minus square root of 2 over 4, all divided by, and then cosine was this one. So square root of 6 plus square root of 2 over 4. So when you have the same denominator in both of these things that you're dividing, they basically cancel each other out. Or you could rewrite this as multiplying by the reciprocal, but either way you'll get to this answer. You'll get to square root of 6 minus 2 divided by square root of 6 plus 2. And I know it looks like you should be able to simplify this, but there actually is no way to simplify this. It's kind of like if you have x minus y over x plus y, you just really can't simplify it. It looks like it has kind of the same thing. If it was negative x minus negative y, then you could factor out a negative sign and simplify. But because there's only one thing that's getting flipped around, They're just too different from each other to be able to do any simplification. So that's how we're going to deal with tangent in this class. All right, one last thing I want to do in this video is we're going to use the formula in a slightly different way. So we're going to basically be using angle addition or subtraction to simplify. So what do I mean by that? So let's look at a first example. So one example of how this could be is we could say simplify sine of pi over 2 minus theta. So if we use the angle subtraction formula, we'll have some parts of it will have an actual angle, right, where you can actually evaluate it, and then the other parts will just have theta. And so we won't be able to get an answer, or sorry, a number as our final answer, but at least some parts of it will be numbers, so we'll end up with a fairly simple answer. Okay, so sine of pi over 2 minus theta, according to our angle subtraction formula, that should be equal to sine of pi over 2 times cosine of theta minus, and now we take cosine of pi over 2 times sine of theta. Okay, so what are sine and cosine of pi over 2? Well, pi over 2 is a 90-degree angle. And so our coordinates of that point are 0 and 1. So that tells us that sine of pi over 2 is 1. So we get 1 times cosine of theta. And then what is cosine of pi over 2? Well, cosine of pi over 2 is the x-coordinate, and that's 0. And so that tells us that this simplifies to just being cosine of theta. So this is actually an identity. So the fact that, so we started with sine of pi over 2 minus theta, and we simplified it, and we found out that it's actually equal to cosine of theta. And so this is something called the cofunction. It's one of the cofunction identities. And I decided not to cover it in the last section just because, you know, there's so many different identities and we have kind of limited time this quarter, but I just thought I'd bring it up here. So it's basically an identity that kind of allows you to go between sine and cosine. So sine of pi over 2 minus theta is equal to cosine of theta. We just showed that. We just basically proved that that identity is true. So I want to do a couple more along these lines. So let's say we wanted to simplify cosine of t plus pi. So the angle addition formula for cosine tells us that cosine of t plus pi should be equal to cosine of t times cosine of pi minus sine of t times sine of pi. So looking at the unit circle, we want to look now at an angle of pi. So that's here. So that's -1, 0. So cosine of t is -1. So we have -1 times cosine of pi. And then sine of t is, or sorry, sine of pi is equal to 0. So we have minus sine of t, and sorry, I reversed stuff here. Let me rewind. So I should have left the cosine of t part there, right? And then multiplied that with -1. And then the second part, we have minus sine of t times 0. And so we're left with negative cosine of t. So this is basically saying that if you take cosine of an angle and add pi to that angle, you get the negative of what you would get by just taking cosine of the original angle. So this is another identity that we just showed. And actually, I'm going to cut it off there. I think I'll save this next example actually for today's worksheet. So I think it's similar enough that you'll be able to get it just based on what we did today. All right, so that is it for today, and I will see you next time.